In this video, we'll talk about um, problems where we can use Taylor series. So let's not forget Taylor series and Maclaurin series are pretty much the same thing, only when we center it about the origin, it's Maclaurin, and when we center it about any number, it's Taylor series. And here in this table, we actually have some common functions like 1 over 1 minus x, which is expanded as a polynomial to the right and is written as a sum here as well. So 1 over 1 plus x e to the x, also it's a common one. They pretty much show up in many problems. Sine of x, cosine of x, ln of 1 plus x, and so on. So let's see a few places where we can actually use this Taylor series. So we have this limit as x is approaching 0 of x squared plus 2 cosine of x minus 2 over 3x to the fourth. One way we can solve it is to find what's the undetermined operation, which is actually 0 over 0, and we can do L'Hopital. Or we can try to use the Taylor series. So first of all, I see this cosine of x, which we have it written in the table that I showed you. It's equal to 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so on. So if we replace that here, so limit as x is approaching 0 of x squared plus 2 times this whole quantity, so it's 2 minus x squared plus x to the 4 over or 2 of 4 factorial minus 2x to the 6 over 6 factorial plus 2x to the 8 over 8 factorial minus and so on, minus 2 everything over 3x to the 4th. So here I actually don't need these parentheses, so dot 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 minus 2. Now this x squared cancels with this one, and we can write limit as x is approaching 0. I get these 2 cancels with these, and we can separate each of them, or we can divide each of these terms by x to the 4th. So the first term is 2 over 4 factorial x to the 4th over x to the 4th. The next one is, times 3 as well. And then minus 2 over 6 factorial times 3, and then it's x to the 6 divided by x to the 4, that's x to the 2nd. Plus 2 over 8 factorial and times 3, and x to the 8 divided by x to the 4, x to the 4, and so on. Now, all these terms are approaching 0, so the term that it's the answer is 2 over 3 times 4 factorial, which is 1 times 2 times 3 times 4. So it's actually 1 over 36. Now, how else we could solve this problem? Well, we could solve it using L'Hopital. So if you checked first, you get 0 over 0, so we apply L'Hopital once, and we get another 0 over 0, so we apply L'Hopital again. Again, we get 0 over 0, so we apply L'Hopital, and again, and we end up with 1 over 36, the same answer as above, right? These two are the same, but we solve it in a different method. So it's up to you to decide which method works for you now that we know more than one method. And also think about it, this problem could have had a L'Hopital applied 10 times, right? So maybe a Taylor series would be more appropriate. Now let's solve my favorite problem on this topic. So another situation where we use power series is when we differentiate. So f of x equals, and I changed a little bit the problem, so I want f of x, not just e to the x, which we have a table for it and we know what it is, but I want f of x e to ix, where yes, I is that complex number with the condition that I squared is -1. So Let's do all these parts. Differentiate a Taylor series about 0. So it's more popular to say Taylor series about 0 when actually we call it Maclaurin for the following function. So again, we know that in order to calculate this, we have to calculate a few derivatives. So let's do that. So I calculated the first 4 derivatives and the corresponding values for 0. Let's calculate a few more. The fifth derivative is going to be I e to ix. So the fifth derivative at 0 is going to be equal to I. The sixth derivative is going to be negative e to ix. So the sixth derivative at 0 is going to be negative 1. So then the Taylor series for e to ix is going to look like this. F of 0 plus f prime of 0 times x plus f double prime of 0, which is negative 1 over 2 factorial times x squared. Then the next one, minus I over 3 factorial x to the third plus 1 over 4 factorial x to the fourth plus I over 5 factorial x to the fifth minus 1 over 6 factorial x to the sixth. And let's do one more. The seventh derivative is negative I e to ix. So the seventh derivative at 0 is going to be negative I. So here is going to be minus I over 7 factorial x to the 7 plus dot dot dot. So we notice that we have terms in I and without I. I'm going to highlight the ones without I first. And then I'm going to highlight the ones that have I with blue next. And then I'm going to put them together. So this equals 2. 1 minus 1 over 2 factorial x to the second plus 1 over 4 factorial x to the fourth minus 1 over 6 factorial x to the sixth plus dot dot dot. This is one set. And then plus, and I'm going to factor out the I and put the blue one. X minus 1 over 3 factorial x to the third plus 1 over 5 factorial x to the fifth minus 1 over 7 factorial x to the 7 and so on. Now, if we think a little bit of these, just keep them in mind, look over them for a bit, look over this one as well, and now let's skip to the tables and let's see if we identify them. So do you notice how these terms here with x cubed over 3 factorial of x plus x to the fifth over 5 factorial and so on is sine of x, while this one with the x to the second and x to the fourth and the 1 is cosine of x. So what we just proved is that e to ix, it's actually equals to cosine of x plus I sine of x. So this awesome result, e to ix equals cosine of x plus I sine of x. You see, we change from an exponential function, we change into a trigonometric identity or expression. This is Euler's identity. And it's a really cool result that we were actually able to prove it using power series. Now another very nice problem is integrating power series, and what's nice about it is that this integral, if you actually want to calculate integral of e to negative x squared dx, the improper one, the undefined one, you won't be able to solve it. But we can solve it using this power series with Taylor series. So e to x, it's equal to, based on the Taylor series, if you look in the table, it's 1 plus x squared over 2 factorial plus x to the third over 3 factorial. You might want to memorize this one as it shows up a lot in application problems. And so e to negative x squared is going to be 1 minus x squared, and then plus x to the 4th over 2 factorial, and then minus x to the 6 over 3 factorial, and then plus x to the 8 over 4 factorial, and so on. So if we go to our integral, so we have integral from 0 to 0.25, and then we put 1 minus x squared plus x squared to the 4th over 2 factorial minus x to the 6 over 3 factorial plus x to the 8 over 4 factorial minus, and then dx, it's equal to, and we can actually calculate this, right? It's x minus x cubed over 3 plus x to the 5th over, well, the 2 factorial was 0 times 5 minus x to the 7 over 3 factorial times 7 plus x to the 9 over 4 factorial times 9 minus dot dot dot, everything evaluated from 0 to 0.25. And if we evaluate, well, we are lucky we have from 0 to 0.25, so we'll just evaluate the upper limit. So it's 0.25 plus 0.25 to the 3rd over 3 plus 0.25 to the 5th over 2 factorial times 5, and so on. Sorry, here it's a minus. And if we evaluate this piece, we actually get approximately, or we get just for this piece, right, we get equals to 0.24488. Now, the actual value is equal to 0.244888. This was calculated with a TI-84. And so if we calculate the error, is actually 0.24488 minus 0.244888. It's in absolute value, so no matter which direction you go, you get 10 to negative 5. So to ensure the error is less than 10 to negative 4, how many terms we should retain? Well, we retain 3 terms. So if I want the error to be within less than 10 to negative 4, let's try just the first 2 terms and see what do we get. So we get 0.25 minus 0.25 to the 3rd over 3. This is 0.244791666. And if we calculate the error is equal to absolute value of 0.2244888 minus, or actually 38 minus 0.244791666. Let's see, I want to have enough 2419 just to have this 6 decimals. So this is equal to 0.000096, which is 0.0001, right? Or 10 to negative 4. So basically, how many terms we should retain? 2 terms are enough. And now another nice problem. Use an approximate representing real numbers. So use an appropriate Taylor series to find the first 4 non-zero terms of an infinite series that is equal to the following numbers. And we have e to the 2nd. Well, obviously, the Taylor series that I'm thinking of, it's e to the x, which is 1 plus x squared over 2 plus x to the 3rd over 3 factorial, which is 6, plus dot dot dot. So e to the 2nd is going to be 1 plus 2 to the 2nd over 2 plus 2 to the 3rd over 6 plus dot dot dot, which is 1 plus 2 plus 4 over 2, which is 2, plus 8 over 6. They said 4 non-zero, so we did 4 of them, so it's 5 plus 8 over 6, which is equal to 6.3 repeated.